Good morning, dear students. My name is Ferhan Mazher, and the subject today we are studying is Cambridge O Levels Physics 5054. Today we have set our hearts to solve paper 4, and we call it ATP, Alternative to Practical. The time allowed for this paper is 1 hour. We have selected May-June 2023 4-1 paper, and this paper 4 belongs from the Zone 1. So let's start. So here we have today's paper, and the time allowed is 1 hour. The total marks for this paper are 40. And here we go. Question number 1. A student investigates specific heat capacity. He puts 25 centimeter cube of water in a beaker. The thermometer in the figure 1.1 shows the temperature theta 1 of the water. Record theta 1. So how much is this reading? Let me increase the size so you can see it clearly. So can you see how much is this reading? This reading is approximately, this is 15, 16, 17, 18. So I think it is 18 degrees centigrade. The temperature shown here is, I think, 18 degree centigrade. So let me, okay. So let's check from here. 18 degrees centigrade is the answer, sir. So our answer is right. So the B part. The teacher has placed some 50 gram masses in boiling water. Each mass has been tied to a length of string. The student takes the beaker of the water to where the masses are in the boiling water. He uses the string to remove one mass from the boiling water and places it carefully into the beaker as shown in the figure 1.2. So this is 50 gram mass. It is tied with a string. It was in the boiling water, and you have taken it by the string from that boiling water, and you have put it into the other water, which was in the beaker, and its temperature was 18 degrees centigrade. So now this mass is very hot. It was in the boiling water. He then returns to his workstation and replaces the thermometer in the beaker. He puts the beaker again in that water. The thermometer in the figure 1.3 shows the maximum temperature theta 2 of the water. Calculate the temperature change. So this is the theta 2. So let me check first of all, how much is this? Can you see how much is this temperature? This is 21, 22, 23, 24, 25, 26. So this temperature is approximately 26. So you have to tell how much is the change. The theta 1 was 18, the theta 2 is now 26. So you have to tell what is the difference of the temperature. So theta 2 is 26. So the temperature change will be 26 minus 18, and that will be 8 degrees centigrade. So the change in the temperature is 8 degrees centigrade. Then he says, this is the second part. He says, describe how to ensure that theta 2 is measured as accurately as possible. So how you can make sure that the temperature of that water in which you have put that 100 gram mass, you measure it very accurately. So whenever you want to measure the temperature of the water, the bulb of the thermometer should not touch the bottom of the beaker. It should be in the middle of the water body. And you should give some time. Always do not note down the reading of the temperature immediately. Give it some time. Okay. So the thermometer can respond to that temperature. You see, when you will put a thermometer into a hot water, do not immediately note down what is the temperature. You let the thermometer respond to that temperature. So what will happen? The level in the thermometer will rise, of the mercury will rise, and you will wait that, let that level of the mercury goes to its highest point. And when it becomes steady or it starts coming down, you note the highest point of the mercury. and that shows the temperature. This is how you do it more accurately. I have written an answer. I have written allow time before taking reading from thermometer to make it rising level steady. So the level of the mercury in the thermometer is rising. So you wait until that rising level becomes steady. Make sure thermometer do not touch walls or bottom of the beaker. So you have to make sure this. So question number 1B and second part, the marking scheme is showing up on your screen. If you want to read it, you can pause the video. Okay. Then we have the third part. The beaker is made from a special type of glass, suggests why it is suitable for this experiment. The beakers which are used for such experiments, they are heat resistant. It means they do not break when you heat them or when you put hot water in them. They do not break. So we will use that kind of beaker which is heat resistant, which can bear that heat. Material of the beaker must be heat resistant so that it do not break on heating, or when you pour hot water in it, or when the water in it becomes hot, it should not develop cracks. So let me show you. This is the answer. Okay, so then we have the fourth part. He says calculate the specific heat capacity of the 50-gram mass using the equation. So the equation is given. In this equation, the specific heat capacity is equal to 4.2 bracket theta 2 minus theta 1 bracket close divided by the 2 and bracket start 100 minus theta 2 bracket close. Theta 2 is 26, theta 1 is 18. Just put those values here and you will be able to calculate the value of the specific heat capacity. So the change in the temperature is 8, 4.2 into 8, and in the denominator you will write 2 bracket start 100 minus 26. So you will have, at the end you will get 0.23. So the specific heat capacity of that material is 0.23 joules per gram per degree centigrade. Our answer is right. Okay, this is C first part. Describe two sources of error in the method used to determine the specific heat capacity. In this method, you know from that formula that basically we are dependent on two readings, two measurements, theta 1 and the theta 2. So the possible errors can be when you are reading the temperature from the thermometer, or when you are using the thermometer, you might do something wrong. For example, if the bulb of the thermometer touch the bottom of the beaker, or if the bulb of the thermometer touch the side of the beaker, then it will not note down the temperature of the water. It will start noting down the temperature of the bottom of the beaker, or you can say the material of the beaker. Another thing can be there might be parallax error. Parallax error is that when you take reading from a scale, the scale on the thermometer, if the line of sight is not perpendicular to the point from where the reading is being taken from the scale, then due to the wrong positioning of the eye, you will automatically naturally note down the wrong reading. This is called parallax error. So these two errors can be there. Heat. Oh yeah, there are other things also. You know, when you transfer that hot mass from the boiling water to your the beaker in which you have water, and you take that mass from the hot water and you put it into another beaker. So when you do this, maybe some hot water is also transferred with that mass, because that hot water will have that mass. Another thing can be because in the story he told us that he went from one place to another place in his lab. He went from one table to another table, and from there he put that hot mass tied with the string from the boiling water. He took it out and put it into the water, and then he comes back to his workstation. So obviously, during this process, he has some time will pass, and the object would have lost some heat to the surrounding. These can also be the reasons. Heat loss from the mass during the transfer, and hot water transferred with the mass into the beaker. Okay, then let me show you this is the marking scheme. You can pause the video, you can read this answer. I hope you can write a better answer. So just two improvements to the method. This is the C second part. So how you can improve this? You see, when you add the mass, you take it out from the boiling water and you put it into the beaker, which has a simple water, normal temperature water, I mean. You shake the mass before adding it into the beaker, so that if it has extra water on its surface, it is shaken off. Another thing you can do is you can bring that uh, the boiling water where the mass is in the boiling water, you can bring that apparatus near your workstation. So place the boiling water near the beaker, so where you are working, and shake mass gently before adding to water. So I hope you understand. There can be many reasons and many explanations, but you only have to write one. So you can read this, you can pause the video. Okay, so we are going to the next question. The next question is question number 2. He says a student investigates a thermistor using a circuit, figure 2.1. So here we have a circuit, here we have 3 cells, and here we have a switch, here we have a resistor, here we have a thermistor, and parallel to the thermistor, we have connected a voltmeter. Okay, draw a circuit diagram of the circuit. So I have to represent this on a circuit diagram. So here, this is that battery, the 3 cells. Here we have the switch. Here we have the fixed resistor. Here is the thermistor. And across the thermistor, we have connected parallel to the thermistor, we have connected a voltmeter. So hopefully you understand. Okay, so question number 2, and it's B part. He says, the student measures the temperature of the room and records it. The recorded result is shown in the figure 2.2. So the room temperature in which they are doing this experiment is 20 degrees centigrade. Okay. Figure 2.3 shows the reading of the voltmeter on the VW on the voltmeter when the switch is closed. So the reading right now is how much? This is exactly 2 volt. So the reading is exactly 2 volt. So let me show you. I have noted it. Yeah. The reading is 2 volt. This is the answer. Okay. Then we have the question number 2. There is a beaker containing ice and water near the thermistor. The student measures the temperature Tc of the ice and water and records it. The recorded result is shown in the figure 2.4. The temperature is 0 degrees centigrade. The thermistor is placed in the beaker of ice and water, and after a minute, the voltmeter is read again. Figure 2.5 shows the reading on the voltmeter when the thermistor is in the beaker of ice and water. So record the reading VC when the voltmeter is in that ice and liquid solution or mixture. So the reading shown by the voltmeter is this much. This is 2.9. 2.9 volt. 2.9 volt. Then he says calculate the average change in voltage for 1 degree temperature change. That is change in the voltage using the equation. Okay, so this is Vc minus Vw divided by Tw minus Tc. State the unit of the answer. So Vc value I know, Vw value I know, Tw value I know, Tc value I know. So I will simply just put those values here. Vc, when the thermistor was in the ice and water solution, the Vc value was 2.9. Vw, when it was on the room temperature, the Vw reading was 2. And Tw is 20 and Tc is 0. So just put those values, do this calculation, you will get 0.045 volt per degree centigrade. This is the unit, volt per degree centigrade. So you can see this. I hope you understand. Use your answer to D first part to predict the voltage VPB across the thermistor when the thermistor is at body temperature. The body temperature is 37 degrees centigrade. You may assume that the average change in the voltage for 1 degree temperature change and delta V is constant. Okay. Now you see it's a little tricky story. Okay. So I'm going to use this equation, the voltage when the thermistor is in the ice and minus the VPB when the thermistor is at the body temperature. Here is the temperature of the body and minus the temperature of the ice, that ice and water. The delta V remains the same as in the previous part. Just put these values, get the value of the VPB, this V value. So just put these values, do the calculation. So the VPB will be equals to 1.235. 1.235. 1.23, I can say 1.2. Our answer is right. This is the answer. The student is told that if the thermistor is held between a thumb and forefinger for 2 minutes, the reading on the voltmeter VAB will be the same as predicted voltage VPB in the D second part. The two quantities are considered to be equal within the limits of experimental accuracy if their values are within the 10% of each other. The thermistor is held between the student's thumb and forefinger for 2 minutes, and the student reads and records the voltage VAB. The recorded results is shown in the figure 2.6. So the VAB when the thermistor is in your fingers for 2 minutes is 0.80 volt. Okay. State whether the student's results indicated that the VPB and the VAB are equal within the limit of experimental accuracy. You see the VAB value is 0.80 volt and the VPB value is how much? That is 1.235. Okay, so the VAB is 0.8 and the VPB value is 1.2, you can say. So let's find the 8% of 0.8. That will be 10, sorry, I said 8. 10% of the 0.8 and it will be 10 by 100 is 0. That is 0.08. So that means the VAB value, which is 0.8 volt, and if I add in it 0.08, I get 0.88. If I from 0.8 subtract this value, I get 0.72. So if this is the right value, it's 10% above and 10% below will be from 0.72 to 0.88. But the VPB value is 1.2, which is not in this range. So it means that the value of the VPB and the VAB are not here. This is the word are. The VPB and the VAB are, this word is are not within limit of experimental accuracy. So they are not same. I hope you understand. This is how it has been done. Okay. Question number 3. A student investigates a falling mass. The student uses the apparatus shown in the figure 3.1. So here we have a hanger A. So you can put mass here. It is tied to a string, sorry, and that passes over a pulley and is attached to another mass hanger B. So this pulley is held by a clamp, and here we have a heavy weight on this stand, so it do not topple to the left, and this is on the bench, on the top of a bench. He says the bottom of the mass hanger A is at a height small h above the floor as shown in the figure 3.1. The student places one end of a meter rule on the floor and the other end near to the mass hanger. The top of the meter rule is shown in the figure 3.2. So here is the mass hanger, here is the meter rule. A meter rule means it's a 100 centimeter meter rule. So the bottom of the mass hanger A is at 1 centimeter mark. So that means its height from the floor is 100 minus 1, and that will be 99. So very simple. Height of that hanger A is 100 minus 1. It will be 99 centimeter. Then he says, describe one source of error when measuring H and suggest one improvement to the procedure to reduce this error. You see, whenever you will find the height of the bottom of that hanger A, so you are using a vertical scale. That vertical scale must be perpendicular to the, or it must be perfectly vertical. Or you can say it must be perpendicular to the floor. So how you make sure that it is perpendicular to the floor? By using a set square. By the help of using a set square, you will make sure that the vertical scale is exactly perpendicular, or you can say it's exactly vertical to the floor. Then another possibility is the source of error can be if you will hold that scale in your hand and that scale will continuously be shaking. If you want that scale to be very steady, you should use a stand and a clamp to hold that vertical scale so that there is no shaking in the scale. Vertical scale might be not steady and vertical to the ground. So use a set square to make sure scale is vertical to the ground and to make it steady. to make it steady, use a clamp to hold it. Okay. I have given here two reasons. You can see this reason, and then you have these things. Okay. Then we have question number 3B part. The student places a mass M of 5 gram on the mass hanger A. So he puts 5 gram here. And due to this, what happens? A student places a mass M of 5 gram on the mass hanger A. The additional mass causes the mass hanger to descend slowly. The student uses a stopwatch to take 3 readings of the time taken for the mass hanger A to fall to the floor. So when they put 5 gram mass here, so due to the weight of that, this mass hanger slowly goes down. Obviously, this will go up. You are supposed to note down the time taken for this mass hanger A to go from this height to this height. It means the time taken for this hanger to touch the ground. You have to measure that time. Using the stopwatch readings in the figure 3.3, determine an accurate average time for the mass hanger to descend the height edge. So here the 3 times are given, you will add them up and you will divide it with the 3, so you will get the average time. So 6.11 plus 5.87 plus 6.02 equals to divided by 3 equals to. And the time average value will be 6 seconds. 6 seconds is the right answer, sir. The student repeats the time measurement with the different masses placed on hanger A. Record the measurement from the B first part in the table 3.1. Complete the heading and give units. Okay. So here you put a mass which was in grams. Here is the time 1, which will be in seconds, time 2, time 3, and then the average time that its unit is also seconds. Okay. So here you can see gram, second, 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 and second. Okay, we have to put, then their question is, he says, on the grid provided in the page 11. So you have to put the values here. We have already noted it down. From those figures of that, the photos of those stopwatches, I'm noting down T1, T2, T3, 6.1, 5.87, 6.02. And then I have calculated their average, that was 6. I just noted down in that table. Then he says, on the grid provided on the next page 11, plot a graph of the V average on the y-axis against the mass M of the on the x-axis. Draw the best fit curve. Okay, so now they are saying this should go this should be represented on the y-axis, and this mass will be represented on the x-axis. Okay, this is what they're saying. So the value of the time is changing from 2.2 to 6. The value of the mass is changing from 5 to 13. So let me show you the graph. So this is a full page given here. So we have to plot a graph and then we have to draw the best fit curve. Okay. And then we have to describe the relationship between the T average and the M shown by the graph. Okay. So I'm going to draw the graph. So here you can see. So on the x-axis, I have represented the mass. This is 2, this is 4, this is 6 gram, this is 8 gram, this is 10 gram, this is 12 gram, this is 14 gram, and this is 16 gram. On the y-axis, we have represented the T average. So rather, there are 4 centimeters represents 1. Here we have 2, here we have 3, we have 4, 5, and 6. Then we plotted these points. You can see. From that table, I will plot these points. At 5, you will have 6. At 7, you will have 4.2. At 9, you will have 3. At 11, you will have 2.6. And at 13, you will have 2.2. So we will plot these points. You can see I plotted these points. And then I will draw the line of the best fit. So here we are trying to draw a curve of the best fit. So you can see I have joined the points with a smooth curve. And I make sure that the points left on the right, the number of the points left on the right and number of points left on the left side are same. Which try to. This is the line of this is the curve of the best fit, sorry. So if you look at this diagram, I was looking for sorry, there was an interruption in the internet due to which there was some interruption. So we were talking about that what will happen here, what is the relationship between them. So when you I mean half the mass, okay, when you double the mass, the time average do not become half. So they are not inversely proportional to each, but when you can say they are not inversely proportional, you cannot say they are inversely proportional. But you know, they are, when you increase the mass, the time average is decreasing and non-uniformly. Okay. I can write here. This is that part. So by looking at the graph and looking at the data, I can tell you that the T average decreases as the M increases. Rate of the change of the T average per unit mass is not uniform. Okay, it is changing. The gradient of that graph is not uniform. It is changing. Okay. Let me show you. This is the marking scheme. You can pause the video. You can take your time to read that. So we are on the next question. Let me show you that question. That was the question. Question number 3. Now we are on the question number 4, which is the planning question. So here in this question, we have to plan an experiment. He says a student attaches a propeller to an electric motor driven by a 0 to 12 volt DC power supply as shown in the figure 2.4. Okay. So here you have a stand with it. We have a clamp, and here that clamp is holding electric motor. It has propellers with it. It is connected to a variable power supply, whose voltage changes from 0 to 12 volt. And here we have an electronic balance. So when the propeller will rotate, when this electric motor will work, the air will be coming on this electronic balance. So this electronic balance will experience a force on its top surface. So due to that, what will happen? It will show some reading. So we will check that reading, and we will check. Moving air from the propeller exerts a force on the balance. Okay. Plan an experiment to investigate how this force varies with the voltage of the power supply. So basically, I'm interested in this voltage here and the reading on the electronic balance. Plan experiment to investigate how this force varies with the voltage of the power supply The following apparatus is available: an electric motor, an electronic balance, a power supply, a propeller, a voltmeter. You can also use other apparatus and material that are usually available in a school laboratory. In your plan, you should explain briefly how to carry out the investigation, state the key variables to control, draw a table with the column headings to show how to display your readings. You are not required to enter any readings in the table. Explain how to use your readings to reach a conclusion. Okay, so my method is very simple. So parallel to this motor, attach a voltmeter and keep the voltage of the power supply on 2, close the switch. This propeller will start rotating. Note down what is the reading on the electronic balance. Then stop it. Then change the voltage on the power supply. For example, it was 2 volt, now make it 4 volt. Close the switch and note down what is the reading due to the force of this air from the fan. Due to that, there will be a reading on electronic balance because it is experiencing a force in downward direction. So note down that reading. Then increase the voltage from the variable power supply from 4 volt to, let's say, 6 volt. Again, note down what is the reading on the electronic balance. So in this way, you are noting down the voltage given to the electric motor or the propeller, and due to the blow of the air from that propeller, the reading given on the electronic balance. You are noting down these two things. Okay, then what are the key things which you need to keep constant is the electric motor should remain same in throughout this experiment. The propeller should be same. It's the propeller size should be same. The electronic balance should be same. The top surface of the balance, the area of the top surface of the balance should be same. The room temperature of this room should be same. The wind in this room should be same. So these are the few factors which should remain same. The power supply should remain the same, although you are changing its voltage. It's a variable power supply. Then you have to draw a column where you will note down the readings. So here we will draw two columns. In the first column, I will note down the voltage given to the electric motor. And on the second column, I will note down the reading, the reading on the electronic balance. So the voltage given to the electric motor, and in the second column, you are noting down the reading on the electronic balance. The reading on the electronic balance is normally in grams. Okay. So let me show you. I have written this. Let me show you the previous question. Okay. So here you can see I have drawn that. Here we have that electronic balance. You can label it. This is electronic balance. This is the propeller. This is the electric motor. This is that stand. This is that clamp. These are the current leads. And here's the switch. Here is the variable power supply. Here, parallel to the motor, I have connected a voltmeter, so I know how much voltage is being provided to the electric motor. So this is my, okay. Then it says, I have written this answer that connect a voltmeter parallel to the propeller. Change the voltage of the variable power supply from 0 to 12 volt by an increment of 2 volt each time. On every value of the voltage, note, here this word is note. Where is that drop? Note the reading shown on electronic balance, and which is placed below the propeller. You have put that electronic balance below the propeller. So its wind is causing a force on the top of the electronic balance. Okay. Every time you do this experiment, distance between the propeller and electronic balance should be same. Top surface of electronic balance should be same. Propeller should be same. Air pressure and room temperature should be same. Direction of the spin of the propeller should be same. The readings of the voltmeter and the electronic balance can be noted in the following table. So you note down what is the voltmeter reading, what is the reading on the electronic balance. Plot a graph between the readings of the electronic balance and voltmeter or electronic balance reading and the voltage reading. Take the reading of electronic balance on the y-axis and the voltage on the x-axis. By looking at the shape of the graph, you can decide the relationship between the reading on the electronic balance and the voltage provided to the propeller. So hopefully you understand this. This is what we have written. So by this question, we have reached the end of this paper. So my dear students, I have tried my best to explain you the concepts in this ATP paper. I hope that you have understood this. If you find this video useful, interesting, and beneficial to you, please share the link of this video with your friends, with your class fellows, with your junior students, whoever are preparing for the Cambridge exam. Please share the link of this video onto your Facebook, onto your Twitter account, onto your TikTok account, onto your Instagram account, onto your X account, onto your LinkedIn account. Because when you do this, this helps me to promote my channel. I think it's a great blessing for me that I can make these videos and I can reach the students who need help online. So it's a great blessing. Thank you very much, everyone. Have a good day. God bless you all.